Good day everyone, my name is Carl Anthony Bueno and I'll be presenting the image formation. The learning objectives this chapter is concerned with the images that result when the light rays encounter flat or curved surfaces between two media. In this chapter, we continue to use the ray approximation and assume light travels in straight lines. Third, we will first study the formation of images by mirror and lenses and techniques for locating an image and determining its size. Then we will investigate how to continue or how to combine these elements into several useful optical instruments such as microscopes and telescopes. Image formation by mirrors can be understood through the analysis of light rays following the wave under reflection model. We begin by considering the simplest possible mirror, the flat mirrors. Consider point source of light lays at O in figure 36.1, a distance p in front of a flat mirror. The distance p is called the object distance. Diverging light rays continue to diverge, or diverging light rays leave the source and are reflected from the mirror. Upon reflection, the rays continue to diverge. The dashed lines in figure 36.1 are extensions of the diverging rays back to a point of intersection at I. The diverging rays appear to the viewer to originate at the point I behind the mirror. Point I appears Point I, which is the distance q behind the mirror, is called the image of the object at O. The distance q is called the image distance. Regardless of the system under study, images can always be located by extending diverging rays back to a point at which they intersect. Images are located either at the point from which a ray of light actually diverge or at the point from which they appear to diverge. Images are classified as real or virtual. A real image is formed with light rays pass through the diverge from the image point, while a virtual image is formed when the light rays do not pass through the image point but only appear to diverge from that point. The image formed by the mirror in figure 36.1 is virtual. The image of the object is seen in a flat mirror is always virtual. Real images can be displayed on a screen or as at a movie theater, but virtual images cannot be displayed on screen. The image of an object seen in a flat mirror is always virtual. Real images can be displayed on a screen as at a movie theater, but virtual images cannot be displayed on screen. We shall see an example of a real image in section 36.2. We can use the simple geometry in active figure 36.2 to examine the properties of the images of extended objects formed by flat mirrors. Even though there are an infinite number of choices of direction in which light rays could leave each point on the object, or represented by the blue arrows, we need to choose only two rays to determine where an image is formed. One of those rays starts at P, follows a path perpendicular to the mirror, and reflects back on itself. The second ray follows the oblique path PR. The second ray follows the perpendicular to the second ray follows the oblique path PR and reflects as shown in active figure 36.2. According to the law of reflection, an observer in front of the mirror would extend the two reflected rays back to the point at which they appear to have originated, which is point P prime, behind the mirror. A continuation of this process for points other than P on the object would result in a virtual image, or represented by the yellow. A continuation of this process for points other than P on the object would result in virtual image, or represented by a yellow arrow, of the inter-object behind the mirror, because triangles PQR and P prime QR are congruent. PQ is equals to P prime Q. So the absolute value of P is equals to the absolute value of Q. Therefore, the image form of an object placed in front of a flat mirror is far behind the mirror as the object is in front of the mirror. The geometry in active figure 36.2 also reveals that the object height h equals the image height H prime. Let us define lateral magnification M of the image as follows. Lateral magnification is equals to the image height all over object height. Lateral magnification is equals to the image height all over object height. This general definition of the lateral magnification for an image from any type of mirror is also valid for images formed by lenses, which we study in section 36.4. For a flat mirror, lateral magnification is equals to +1 for any image because H prime is equals to H. The positive value of the magnification signifies that the image is upright. By upright, we mean that if the object arrows points upward as in active figure 36.2, so does the image arrow. Let's resolve the conceptual example 36.1. Multiple images formed by two mirrors. Two flat mirrors are perpendicular to each other as in figure 36.4, and an object is placed at point O. In this situation, multiple images are formed. Locate the positions of these images. So as you can see, the image of the object is at I1 and mirror 1, or the violet rays, and at I2 in mirror 2, or the blue rays. In addition, a third image is formed at I3, the brown rays. This third image is the image of I1 in mirror 2, or equivalently, the image of I2 in mirror 1. That is the image at I1 or I2, serves as the object for I3. To form this image at I3, the rays reflect twice after leaving the object at O. Hint: when an object is placed in front of two mutually perpendicular mirrors as shown, three images are formed. Follow the different colored light rays to understand the formation of each image. Let's resolve the conceptual example 36.2, the tilting review mirror. Most review mirrors in cars have a day setting and a night setting. The night setting greatly diminishes the intensity of the images so that the lights from trailing vehicles do not temporarily blind the driver. How does such a mirror work? The solution of this problem is that figure 36.5 shows a cross-sectional view of a rear view mirror for each setting. The unit consists of a reflective coating on the back of a wedge of glass in a day setting, or figure 36.5. 5a. The light from the object behind the car strikes the glass wedge at point 1. Most of the light enters the wedge, refracting as it crosses the front surface, and reflects from the back surface to return to the front surface, where it is refracted again as it re-enters the air as ray B for bright. In addition, a small portion of the light is reflected at the front surface of the glass as indicated by ray D, or for dim. This dim reflected light is responsible for the image observed when the mirror is in the night setting in figure 36.5b. In that case, the wedge is rotated so that the path followed by the bright light, or ray B, does not lead to the eye. Instead, the dim light reflected from the front surface of the wedge travels to the eye, and the brightness of trailing headlights does not become a hazard. Hint: cross-sectional views of a review mirror. A. With a day setting, the silvered back surface of the mirror reflects a bright ray B into the driver's eye, while B. With the night setting, the glass of the unsilvered front surface of the mirror reflects a dim ray D into the driver's eye. Images formed by spherical mirrors. In this preceding section, we considered images formed from flat mirrors. Now, we study images formed by curved mirrors. Although a variety of curvatures are possible, we will restrict our investigation to spherical mirrors. As its name implies, a spherical mirror has the shape of a section of a sphere. Concave mirrors. We consider reflection of light from the inner, concave surface of spherical mirror as shown in figure 36.6. This type of reflecting surface is called concave mirror. Figure 36.a shows that the mirror has a radius of curvature r and its center of curvature is point C. Point V is the center of the spherical section, and the line through C and V is called the principal axis of the mirror. If the object distance P and radius of the curve If the object distance P and radius of curvature r are known, we can use figure 36.9 to calculate the image distance P or distance Q by convention. This These distances are measured from point V. Figure 36.9 shows two rays leaving the tip of the object. One of these rays passes through the center of curvature C of the mirror, hitting the mirror perpendicular to the mirror surface and reflecting back on itself. The second ray strikes perpendicular to the mirror surface and reflecting back to itself. If the object distance P and radius of curvature r are known, we can use figure 36.9 to calculate the image distance Q. By convention, these distances are measured from point V. Figure 36.9 shows two rays leaving the tip of the object. One of these rays passes through the center of curvature C of the mirror, hitting the mirror perpendicular to the mirror surface and reflecting back on itself. The second ray strikes the mirror at its center, point V, and reflects as shown. Obeying the law of reflection, the image of the tip of the arrow is located at the point where these two rays intersect. From the large gold right triangle in figure 36.9, we see that the tan theta is equals to h all over p, introduced because the image we see that the tan theta is equals to h all over p, and from the blue right triangle, we see that the tan theta is equals to negative h prime all over q. The negative sign is introduced because the image is inverted, so h prime is taken to the negative. Therefore, from equation 36.1 and this results, we find that the magnification of the image is m is equals to h prime all over h, or is equals to negative q all over p. Also notice from the green right triangle in figure 36.9 and the smaller gold right triangle that tan alpha is equals to negative h prime all over r minus q, and tan alpha is equals to h all over p minus r. Also notice from the green right triangle in figure 36.9, the smaller gold right triangle that tan alpha is equals to negative h prime all over r minus q, and tan alpha is equals to h all over p minus r, from which it follows that h prime all over h is equals to negative r minus q all over p minus r. Comparing equation 36.2 and 36.3 gives r minus q all over p minus r is equals to q all over p. Simple algebra reduces this expression to 1 all over p plus 1 all over q is equals to 2 all over r, which is called the mirror equation. We present a modified version of this equation shortly. If the object is very far from the mirror, that is, if p is much greater than r, that p can be said to approach infinity, then 1 all over p is equal to 0. And equation 36.4 shows that q is equals to r all over 2. That is, when the object is very far from the mirror. The image point is halfway between the center of curvature and the center point of the mirror as shown in figure 36.10a. The incoming rays from the object are essentially parallel in this figure because the source is assumed to be very far from the mirror. The image point in this special case is called the focal point or f, and the image distance the focal length or f, where focal length is equals to r all over 2. Convex mirrors. Figure 36.11 shows the formation of an image by a convex mirror. That is, one silvered so that the light is reflected from the outer, convex surface. It is sometimes called a diverging mirror because the rays from any point on an object diverge after reflection as though they were coming from one point behind the mirror. The image in figure 36.11 is virtual because the reflected rays only appear to originate at the image point as indicated by the dashed lines. Furthermore, the image is always upright and smaller than the object. This type of mirror is often used in stores to foil shoplifters. A single mirror can be used to survey a large field of view because it forms a smaller image of the interior of the store. We do not derive any equation for convex spherical mirrors because equations 36.2, 36.4, and 36.6 can be used for either concave or convex mirrors if we adhere to the following procedure. We will refer to the region in which light rays originate and move toward the mirror as the front side of the mirror and the other side as the back side. For example, in figure 36.9 and 36.11, the side of the left the mirror is the front side and the side of the right of the mirror is back side. Figure 36.12 states the sign conventions for objects and image distances, and table 36.1 summarize the sign conventions for all quantities. One entry in the table, a virtual object, is formally introduced in section 36.4. Ray diagrams of the mirrors. The position and size of image formed by the mirror can be conveniently determined with ray diagrams. This pictorial representation reveals the nature of the image and can be used to check results calculated with the mathematical representation using the mirror and magnification equations. To draw a ray diagram, you must know the position of the object and the location of the mirror's focal point and center of curvature. Table 36.1 Sign conventions for mirrors. Quantity. Object location, positive when object is in front of the mirror on a real object. Negative when object is in back of the mirror or the virtual image or the virtual object rather. Image location or Q, image is in front of a mirror or the real image. Negative when image is in back of the mirror or the virtual image. Image height or the H prime. Image is upright and negative when image is inverted. Focal length or the F and the radius or R. Mirror is concave and negative when mirror is convex. Magnification or M. Image is upright and negative when image is inverted. Ray diagrams for mirror. The position and size of images formed by mirrors can be conveniently determined with ray diagrams. Ray diagrams for concave mirrors. Ray 1 is drawn from the top of the object parallel to the principal axis is reflected through the focal point F. Ray 2 is drawn from the top of the object through the focal point or as if coming from the focal point if P is less than F and is reflected parallel to the principal axis, while ray 3 is drawn from the top of the object through the center of the curvature C or as if coming from the center C if P is less than 2F is reflected back on itself. Ray diagrams for convex mirrors. Ray 1 is drawn from the top of the object parallel from the principal axis and is reflected away from the focal point F. Ray 2 is drawn from the top of the object toward the focal point on the back side of the mirror and is reflected parallel to the principal axis. Ray 3 is drawn from the top of the object toward the center of curvature C on the back side of the mirror and is reflected back on itself. And that ends my presentation. Thank you for watching.